Hello and welcome everybody. Now, as I promised you, for who of watching this video and who has looked at the community tab, you might have known for a while that after my last mechanics video on Newton's laws, I am planning, I was planning the whole time to post some videos about quantum mechanics, and they're getting prepared, and the videos are gonna be so dope. And this is going to be the first video of all of them, so let's get straight into it. Alright, so before we talk about quantum mechanics, let's just, sorry about that. Let's go for reference QM. Alright, what does quantum mechanics mean? Like, so, last video, you basically have an explanation of what mechanics is. Okay, I know what classical mechanics is. In classical mechanics, I know and I can fully predict. For example, I have a planet or I have an object. So let's say I have a ball over here and here's its center of mass. It's gonna go this way if I apply a force of X newtons on it, because that is predictable. Yes, that is true. We can predict that using our equations, where we can say that force equals ma, and I can calculate the acceleration F over m, and I can conclude using a force sensor. These are things that we have fully established in the 19th and the 17th century with Newton and Galileo when they spoke about classical mechanics. But there was a gap. We always thought that we could predict everything. We can predict the motion of planets, Kepler's laws, Newton's law of universal gravitation. But there was a gap, guys. We started to look deeper. We started to realize that our theory isn't complete. And why we thought that? Because we started to think of something called atoms. Yep, what are atoms? When we finished the classical theory of, classical physics, we had to invent a new tool that could help us to describe what happens at the atomic level. Why? Because classical mechanics cannot be applied. Around the year 1900, there was a guy that was called Rutherford, right? And this guy that was called Rutherford, he had an idea for what an atom is exactly. He told you that in his theory, now obviously his theory is well studied by many physicists, so I can't go over all of it in one video, but I'll give you a small explanation because there's another physicist called Niels Bohr. So he told you that there is something called a nucleus, and it is a bunch of particles clamped up into each other, right? And they have these things, small things, very small things that carry a negative charge. Sorry, the electron has to be a bit smaller. And these things are called E negative. E negative. What is E negative? That's just a short mathematical term for the word electron. Electron. And this is nothing but, you knew this from science class, this is nothing but the nucleus. Now, Rutherford told you, okay, guys, we have a theory of the atom. Okay, so don't we try to, apply classical mechanics? Let's see perhaps if we can use force and stuff. Whoa. Okay, we have to enhance our understanding of the atom before we apply anything, right? So, cometh a new man called Niels Bohr. And matter of fact, Niels Bohr and Einstein, Paul Dirac, many of the physicists that I'll mention in this video, they are one of the most brilliant people in the world because they put the foundation for quantum mechanics. Anyways, so Niels Bohr told you, okay, Rutherford, I agree with you, but we have to enhance our stuff a bit. You told us that we have something called the nucleus. Bohr said, okay, no problem. You have in it stuff called protons, P positive, and you have something that has no electrical charge called N, neutrons. And I wrote positive negative because that means that it is neither positive or it is neither negative, which is why the atom is electrically stable. It's not either too positive or too negative, because if there was a difference, Then if the nucleus, for example, was too positive, then the electrons would just, get smushed, because, in classical physics, now this might be an application, sorry. In classical physics, you have a magnet or some electrical charge. Here's a particle that has some negative electrical charge, and here's a particle that has some positive electrical charge. Using Coulomb's law, what is Coulomb's law, if you've learned it? It basically says that the force of electric here is nothing but the Coulomb constant multiplied by the charge of the first particle multiplied by the charge of the second particle, all of that over the radius squared, but in an absolute value. And we can use this equation from classical physics to describe the electric charge, and thus we prove that positive, there's a force here, it attracts. This guy exerts an electrical force, Fe, and it attracts this guy. So, different charges attract, same charges repel. We proved that. Coulomb's law, Ohm's law, and electrical resistance, and a bunch of things. So, now we know that. We know neutrons and stuff. Bohr said, hey, we have to enhance our theory a bit. Like we said, electrons, right? They orbit. A new term, right? They orbit, because we just saw that they just go around and stuff in the atom. We didn't know where they were exactly. And now they go in something called atomical orbits. Oh, now that's something new, Mr. Niels Bohr. How'd you figure that out? He figured it out using a bunch of things. But we'll go over that in the next video, because this is just the start of, I'm giving you an introduction to quantum mechanics. Quantum mechanics, you can't just fit it all into one video. And you'll see that I'm talking about a bunch of things in one time, so bear with me. So here you have your electrons. And you've got your protons and your neutrons in the nucleus. Bohr said, okay guys, now we have a kind of a better theory of understanding how the atom is built. And this is actually true. And we've proved that later on. Yes, the electrons have atomical orbits, and yes, sorry. Alright, sorry about that, everybody. So now, as we were saying and talking about the Bohr model of the atom, we now are going to attempt to apply classical mechanics. Alright, something you have to know, and I know that every word I say there is an explanation for it, and listen, that's just how quantum mechanics is. I'm sorry, that's how quantum mechanics is. You need to know a lot of principles. You can't just go and burst and get it. No, that's not how it works. So, each particle has a wavelength. For example, let's draw the y and the x-axis. You took that in your science class, that for example, if I have some water source here, this is a pond of water, say, and if I drop, for example, a rock over here, all of a sudden, boom, some ripples will form in the water in every direction, right? You'll see that in real life. That is called a wave, and particles exhibit this same nature. And you'll learn in quantum mechanics how exactly do they do that. Something called the wave function, and it's called psi of x, this letter. Anyways, forget psi of x and forget wave function. Let's get back to where we were. So the electron has a wavelength, alright? And the wavelength is nothing but the distance, sorry, I should do this. The distance either between a top. You see, this is a top, two tops, or two crests. Now, I didn't draw another crest. Here's a crest, but here's a top. So this is called the wavelength, and it has this letter called lambda, right? Now, as we were saying, if we attempt to apply classical mechanics here, the wavelength of the electron emits some sort of electromagnetic radiation. Now, you took that light is also composed of many colors, white light, It's composed of many colors, and you have red, you have green, orange, and so on. Each one has some sort of wavelength, and each one has its own radiation. And light, as itself, is some sort of electromagnetic radiation. Now, if you don't understand what the term electromagnetic is, just think of it as waves, and think of it as light mainly. Why? Because electromagnetic means something that just can travel through space. It can just travel through anything. It doesn't need a medium to travel through. Sorry guys, so as we were saying, think of electromagnetic, like I told you, as some sort of wave. There are longitudinal waves, and those are the ones that, such as sound. Sound needs a medium to travel to. Now, what is a medium? A medium such as air, some air molecules. Sound can vibrate through them and just casually transport through them. And you have, for example, I don't know, maybe in solids, sound travels faster because the vibrations are much stronger. So now you have an idea of what a medium is. And light doesn't need a medium to travel through. That's why it has electromagnetic radiation. Electromagnetic, M magnetic, and radiation. So the electron also exhibits the same behavior. It has EMR. And if you attempt to apply classical mechanics in this case, you'll see that as it emits this electromagnetic radiation everywhere, and just, this radiation can be in the form of X-rays or particles, depending on the type of, electron. Yes, there are types of electrons, positron stuff. As it keeps emitting radiation and emitting, it will crash into the nucleus. Why? Because it lost a lot of kinetic energy. And as I said, there's already, like, the way the atom is, how it is designed by God, is that God made the atom, like the electrons, at such fixed orbits so that the electrons don't get too much affected by the electrostatic force between the nucleus, because this is positive, electric charge, and this is negative. So, it's designed this way. Don't tell me there's no creator, bro. But anyways, aside from religion, as I was saying, this proves that you cannot apply classical mechanics, because as you said, we tried to describe its velocity and its position, its momentum, everything using classical mechanics. And if you attempt to apply, for example, I don't know, Newton's law of universal gravitation or some magnetic classical laws, you'll see that when you apply it, no, it just doesn't work. It doesn't apply. So physicists came to a conclusion, guys, oh my god, we have a gap in our knowledge. We need a new tool, and that new tool is called quantum mechanics. Alright everybody, and now that we have established what is the whole idea of why, there's another why, there's another what, there's another how. There are a bunch of questions. So physicists around the 1900s, like I told you, realized, oh my god, Rutherford, what do we do? I don't know, Bohr, what do we do, Gilman, what do you do, Einstein? And Einstein also was very, very, very insane with his theory of relativity, which also goes in hands with quantum mechanics. Now, in quantum mechanics, you have to realize that every calculation you make is going to be a bit rough. Each particle isn't like you think, because remember, our whole life, we thought for nearly 300 years, since the revolution of science in the days of Copernicus and Galileo, that everything works like a running clock using classical mechanics. Quantum mechanics, everything's different. So let's think of how we realized the catastrophe that we had. We already realized the catastrophe that, oh my god, we can't describe what's going on. We don't have a complete theory of what happens of physics. There was a guy called Max Planck. Alright, Max Planck. So Max Planck told you, I'm gonna suppose that I have these bodies, alright? And they are gonna be called black bodies. These bodies actually weren't just hypothesized by Planck. They were also hypothesized by some other physicists. Personally, I can't remember his name right now, so let's stick with Planck. So Max Planck told you, I have these black bodies. Now you're wondering, okay, go on. I'm with. So these black bodies, Planck said, okay guys, I'm gonna come up with a theory that is gonna help us to use this new tool, and I'm gonna call it quantum mechanics. People say how. People say, and Planck says, I have something called black bodies. These black bodies, they're called black because, okay, how is something black? For example, guys, I'm gonna ask you a quick question. If you're in summer, it's the hottest summer ever, and you're going in the street, what color of shirt or t-shirt you're gonna want to wear so you don't feel as hot as you want to? Take a second. And you have two answers, white or black. If you chose white, congratulations, you're correct. If you chose black, you're wrong. Tell you why. Because of this idea, black, the color black itself, this, get another different color. So it's this. I know I'm being a bit weird, but the color black, this guy over here, this man, color black, it is able to absorb nearly all of the light that is, I'm sorry, how to say? Oh, yeah, it absorbs all of the wavelengths of light. And like I said, there are different colors of light and so on, and there are different wavelengths. For example, there's something called infrared light. Infrared. Let's try that. Infrared light. Now, this infrared light, you might have heard of it before, maybe perhaps in science class, but infrared light is a type of wavelength as well. It has, I think, very small wavelength, and it is kind of the hot part of light. Yes, you think light is just the brightness. No, light also has some heat. How do we get energy from the sun, guys? It doesn't just come in forms of light. No, we have gamma rays, we have X-rays, we have many things that are emitted towards the sun. Solar storms and stuff. Anyway, so we have this part called infrared light. This infrared light has to do with heat. So if you were black, you're gonna take all of the infrared light and it's gonna come towards you, and you're gonna feel all of the heat that is coming towards you from the very bright and beautiful sun. All of the heat, all of the light, all of the colors, all of them going towards you. So that's why we call it a black body, because they absorb all because they absorb all of the light. They absorb, oh, what was sorry about that. They absorb all of the wavelengths. But regularly, if you wear a black t-shirt, you know, you're gonna absorb them, but you're also gonna emit some back. This guy is selfish. This black body does not. This black body over here doesn't. Yes. It doesn't emit back any radiation. Sorry, not any radiation. It does have, sorry. It doesn't emit back any of the wavelengths. That's why it's called black body. And its radiation can be thought of these things that are called quantas of energy. So, Max Planck said, okay guys, I have black bodies. Okay, Black Planck, what are your ideas about them? Like, do you just think of them all of a sudden? No, guys, there must be some tool in the way that they absorb the electromagnetic radiation from the white light, and somehow they also emit it. What's it called, guys? What should we call it? They said, Planck, how do you just know that the black body radiation just, you know, does that by these small things? He said it must be. It must be, and that is true. Otherwise, this hypothesis wouldn't even make sense. And I know, speak up, it's a hypothesis. It shouldn't even be real. Sorry, but as I was saying, speak up, it's a hypothesis. It already shouldn't be. No. Just because something is a hypothesis, that doesn't mean it's not necessarily real. Oh, English. Anyway, so, as I said, he said that if it weren't for these quantas of energy, so now we're getting somewhere. These packets, these discrete small packets of energy, Max Planck referred to them as quantas of energy, which are very small and nearly massless packets of energy. And that is the way that black bodies absorb the electromagnetic radiation and they emit. And now here's a question that a lot of people might ask. You guys might have heard of black holes, and no, it has a lot of stuff. But people are gonna say, hey, don't black holes do the same thing? I mean, they're already black, partially of what you're saying is correct. A black hole can be a near black body, but it does not meet the capabilities. Why? Because some of things. There are some conditions for you to be called a black body. Like I said, you would need to absorb all of the radiation coming towards you, right? Radiation. And you need to not emit any back. So you don't emit. But the black hole does that. That's what the black hole does. The black hole, in matter of fact, no. The black hole does emit nearly all of the radiation back. And it also spews out some gas and some mass that it doesn't need over time. The black hole just keeps shrinking and shrinking till it dies. It emits it in something called Hawking radiation. And it's a long story, but that's why the sorry guys. That's why black holes aren't considered black body radiation. No, not equal black body. So another reason why is because black bodies need to have a uniform temperature. They need to have a constant temperature. You can't just have a change of temperature. No, constant temperature, like constant velocity, zero acceleration, constant acceleration, kinematic equations, all of that. You need to have constant temperature. Delta T just means change in temperature. In this case, for the black body, it's going to be equal to 0. Okay? And if we, and I don't know if I'm able to make this correctly, but if we can draw the relation between the spectral radiance of, like, the radiation of the black body, so let's refer to it as S, and here the wavelength, lambda, actually no, not the wavelength, sorry, what's it called? Sorry guys, give me a sec. Alright guys, sorry. So we're back, and as I was saying, there is a relation between two things in Planck's law, used to describe the black body radiation. Now, as you see, there is an inverse relationship between lambda, the wavelength of the electromagnetic radiation that the black body emits, and its spectral radiance, which is the radiation itself. As you see, the higher the wavelength increases, the less the spectral radiance is. And here's the thing you have to realize, is that something I actually forgot to tell you about in black holes. Another reason why black holes can be black bodies, because in order to, you know, be a black body, you must absorb all. Black holes actually are not able to interact or absorb the wavelength emitted by low energy photons. And why am I saying, what is low energy photons? Photon, I'll tell you right now, it's basically the packet of energy. But as I was saying, it can't interact with it. But how? I thought black holes, dense space-time. Shh. Let me finish. Because the higher the wavelength of the particle that you have, or the radiation that you're emitting, the higher it gets, the less you will be able to interact with matter. Hence the applications of that in real life. We have 5G, 6G, we have to make the wavelength less, and the frequency so high to the point where it just casually interacts with everything, and 5G can go through walls, and the photons are much faster, so the connection is higher. That's the real application of electromagnetic radiation from the black body radiation. Even though it's a hypothesized idea, look, it still has applications. Isn't physics just wonderful? Now, as we were saying, the higher the wavelengths, the less the spectral radiance. Alright? But if we decide to make a relationship between the spectral radiance, alright, and the temperature in kelvins, alright, spectral radiance, you'll see that it is a direct relationship. Kind of. The higher your temperature is in Kelvin, the higher radiation you'll emit. And you'll see that near stars. For example, the amount of radiation that our sun can emit is less than the amount of radiation that a much more energetic star can emit, a much more hotter star, right? Now, since we have, kind of understood what is black body radiation, kind of, I know I might have misinterpreted some things in the middle, but I hope you understand. So you're still gonna ask me, okay, Seeka, but after all this, how? Pay attention to what I said in the video. In order for these black bodies to even, hypothesis to exist, they have to absorb and emit radiation, something called photons. Photons, but I thought, yes, photons were nothing but these quantities of energy. And look, they were hypothesized. Photons have now been fully discovered, and they are a true thing. They are particles. So Max Planck was right about these hypotheses. So, in the year 1900, after all of this, physicists are going insane, man. Oh my god, we actually are about to start to use this new tool to describe. But how exactly? In the 1900s, there was something called the ultraviolet catastrophe. The ultraviolet... focus on the word catastrophe, remember? Catastrophe. Yes, I know, my handwriting is terrible. It's only terrible when I write English. When I'm writing math symbols, it's very beautiful, like EMR and EMF. Anyways, so this ultraviolet catastrophe came to physicists, and they said, hey, Max Planck, you got it all wrong, bro. The equation's wrong. Everything's wrong. Max Planck said, no, let me correct it. And Max Planck corrected it, and he proved that there are discrete packets of energy called quantities of energy, or as we now know them as photons. And this just proved that these photons, we will be able to use them as a tool to enter quantum mechanics. We actually are about to delve deeper into this realm of the unknown. Now, before I leave, there is an idea that I can tell you about in quantum mechanics, but I mean, I don't know, guys, but I think I should give the next video because this video has gone a lot longer right now. But just so you know, if you're still confused how we are still gonna apply quantum mechanics, I'll tell you in the next video. And the next video, there's gonna be a tripod, there's gonna be a ring light, we're gonna do a face reveal, and it's gonna be an insane video. Just make sure to be tuned and have a good day, guys. And make sure, hey, if you're a Muslim, Ramadan Mubarak. It's last 10 nights of Ramadan, so Laylatul Qadr might be somewhere in there. Make sure to pray Tarawih, read Quran as much as you can, do your best. Inshallah, Allah will forgive all your sins and grant you Jannat al-Firdaus. Peace.